All right, on this slide, we're going to see how to compute the Gibbs free energy of the reaction from our electromotive force, both in the standard state. We've already seen that the Gibbs free energy of reaction just equals negative number of electrons transferred in the reaction times Faraday's constant multiplied times that electromotive force. Okay, so that immediately answers this question right here. And by the way, remember that the Gibbs free energy of reaction also equals negative RT log equilibrium constant, like that. So that's why we're able to just set these two things directly equal to each other. And we've already seen this equation before. That just implies the following. And we saw that one in the previous lecture. So then what about finding the entropy of reaction from the electromotive force? Well, for chemical reactions occurring in solutions, we can say that the derivative with respect to temperature of the Gibbs free energy at constant pressure is going to be equal to the negative entropy of reaction, like so. And that's because we're assuming that the enthalpy, so delta H with respect to T at constant pressure, is going to equal 0. We're assuming that the enthalpy doesn't really change at all with temperature, and that's a mostly valid assumption, and it's a perfectly valid assumption to make for reactions that are occurring in solutions. So anyways, there you have it. We can plug in our derivative from here directly into this spot over here. We can pull out the n, we can pull out the f, because those are constants. So as a result, we can say the entropy is going to equal NF, the derivative of that electromotive force with respect to temperature at constant pressure. So this quantity right here is probably something you would have to be given. Maybe it could be measured experimentally. Although if you were equipped with a theory that had an equation for the electromotive force as it relates to temperature, then you could calculate this derivative mathematically. I would like to just show you a brief calculation of the sort that you might do. Let's consider the reaction that we were looking at on the previous slide. Okay, I would just like to point out to you that N in this case equals 6, because there are 6 electrons that are being transferred in this reaction. This zinc has a +2 charge, and there's 3 of them, and then it ends up with 0 charge on that side, so therefore 6 electrons must have been transferred. So that is the N that we would plug into this equation in order to calculate what the Gibbs free energy would be from the electromotive force. We could plug in Faraday's constant, and then we could plug in the electromotive force that we found on the previous slide. Okay, I'd like to review a nomenclature that you learned in general chemistry for talking about electrochemical cells. So imagine that we had the following reaction: solid zinc as the terminal for the electrochemical cell. Then we have copper sulfate in the other cell. The zinc is being oxidized to zinc sulfate, and it's forming copper metal. This just happens to be the so-called Daniell cell with 2 L's. Daniell cell. That's this particular reaction. Okay, so which of these reactions are occurring at the anode for the cell? Now remember, anode is oxidation. And it looks to me like the zinc is what's being oxidized. And the cathode is clearly the copper because it's being reduced. Remember, A is a vowel, so is oxidation. C is a consonant, so is reduction. So then for the nomenclature, what we have to do is we have to put 2 bars representing the junction between the anode and the cathode. And we have to put the anode on the left side of those 2 bars, and we have to put the cathode on the right side of those 2 bars. Hopefully this one is familiar. And we put the oxidized form up closest to the double bar, and then we put a single bar, and then we have the reduced form. I'm forgetting the phase here. Okay, zinc solid, and then this bar solid copper, like so. Okay, and that's it. That's the nomenclature that's indicating the particular type of reaction that is occurring within the cell. Now, what if the terminal is not composed of the same substance that is actually in the reaction? For instance, we might have the following reaction. Solid zinc may be reacting with acid to form oxidized aqueous zinc plus H2. I need to balance this. Okay, yeah, so that looks balanced to me. And this is gas. So obviously we can't make a terminal out of gas. So then what's the correct nomenclature for this particular cell? Well, as usual, we have to put the anode on the left, which is the thing being oxidized, and clearly it's the zinc that's being oxidized. So we would put zinc, we'll just assume it's zinc sulfate that is part of the reaction. And we can make a terminal out of zinc, so we would put it right there. And then over here, we have the oxidized form of H+, also aqueous. And then we have the H2 gas right next to that. And then it's convention to make another bar and put the substance that the terminal is composed of beyond that last bar. So let's say that it is a solid platinum terminal, which is what is used in the reference cell. That is how you would write this nomenclature for terminals that are not made of the metal actually reacting.